Now that we have some of the basic terminologies down, talking about probabilities such as complement, disjoint or mutually exclusive, union and intersection down, we want to start talking about these and using these to determine probability. So basically what we want to do is this. There's a sample space. So for instance, if we flip a coin, the sample space is head or tails. What we want to do is we want to assign each of those events, heads or tails, with some probability that associates the likelihood that that event will occur, and again based on long-term relative frequency. So we're trying to associate probabilities with events. So to get started, we need to look at some basic properties of probabilities. Now when we talk about these basic properties of probabilities, these properties will be true for the rest of the semester. Everything that we do in this text, we're assuming that these probabilities are going to follow along with these properties. So the first thing we want to talk about is the fact that every probability has to be between 0 and 1 points inclusive. So here we have the probability of event x. That's what this notation means. P of x is the probability of event x. This is not functional notation. This does not mean take a value of x and plug it into the function p. This means the probability of event x. All probabilities are between 0 and 1. So for instance, if we roll a fair die with number dots on the side from 1 through 6, the probability of rolling an 8 is 0. So I can actually have a probability equal to 0, and I can actually have probability of equal to 1. So a common question on the test is to list these properties, and a lot of times people will list these without the equal signs, but please be aware that probabilities can be between 0 and 1. The next thing that we need to talk about is the sum of the probabilities. So if I flip a coin and I have a head or a tail as a possible outcome, only the two possible outcomes when I flip a coin, the probability of a head plus the probability of a tail has to equal 1. So the sum of the probabilities from the sample space must equal 1. If I flipped a coin and I had the probability of a head was 0.2 and the probability of a tail was 0.3, I'd have another 0.5 hanging out there somewhere for some other event to occur, and I would need to account for it somehow. The third property that I want to talk about is that of the complement. Now we've already talked about the complement in the last section and what it looks like in terms of a Venn diagram, but here we're talking about it in terms of probability. Basically what we're saying is the probability of the complement of event A is 1, because that's the total probability, minus the probability of event A. So the probability of the complement is 1 minus the probability of the event. Now we've also talked about mutually exclusive events. Another name for mutually exclusive, just as a quick review, is disjoint. And we know from the Venn diagram perspective that this basically looks like two events that do not overlap. So event A and event B. So here we'd have to say they have no outcomes in common, just as a quick review. Now remember, another name for mutually exclusive is disjoint. So don't forget, if you see disjoint, that means the same as mutually exclusive. Now we also have events that are not disjoint. So let's go ahead and talk about events that are not disjoint. So that might look something like this picture. We have written plenty of these out. So here's A and here's B. So now what I want to do is I want to talk about the probabilities of events occurring and how they kind of match up with the Venn diagram. So here, if I wanted to talk about the probability of A or B, this would just be the probability of A plus the probability of B. Now again, if I'm going to use my notation A or B, or is going to look like the union symbol. Again, this would be the probability of A plus the probability of B. Now down here, actually let's go ahead and run back up here. That would be just this probability of A is shaded here, the probability of B is shaded here. Now down here that's going to change. The probability of A or B, I would add the probability of A and B just like I did above, but I have a little bit of a problem because when I do the area that I did above, I end up counting this middle part 2 times. So here's the probability of A, and then let's look at the probability of B. It's harder to see here, but I have this shaded region in yellow on the right, green on the left. And what ended up happening here is this got counted with the green and the yellow, so it got counted twice. So what I need to do is I need to subtract one of those counts out. So that would be the probability of A and B. And just to be consistent, let me put an and in here. So here I have the probability of A or B is the probability of A plus the probability of B minus the probability of both, or the and. So these are some formulas that are important to know. Now for this formula, the probability of A or B, if I know 1, 2, 3, 4, there's 4 parts to this formula. If I know 3 out of the 4 parts, I can solve for the 4th. So it's not just good for finding the probability of A or B, it's good for finding any of those parts that might be unknown. Let's go ahead and look at an example. Now this example is 2.14 from your text. And I believe that is on page 60. So let's go ahead and look at an example from your homework to kind of familiarize yourself with some of that. Oops, so this is actually not from your homework. It's from your text though on page 60. It's an example. So for this example, and I'll let you read through it in your text if you'd like, we basically need to get some basic information out of this. And what we get from this is it says 60% of all households get internet service from the local cable company. So 60% of all households get internet from the company. Another piece of information says that 80% get TV service from that company. And you're knowing where this is heading. 50% get both internet and TV from the company. So what we want to look at here are some Venn diagrams, and we're also going to look at how we notate this information using probability notation. So probability of I, probability of internet is 60%, 0.60. Probability of TV is 0.80, and then I have the probability of both. Now both doesn't really help us describe this, so we should say it, instead of just both, we should say internet and TV and get used to this type of notation, and that's 50%. Now from here, wouldn't it be nice if we could set out some sort of a Venn diagram of what this is talking about? So let's go ahead and look at a Venn diagram, and with this Venn diagram we'll be finding some probabilities as well. So instead of events A and B like we've been writing, we're going to have internet and TV. So if we look at internet, that basically means this circle makes up 0.6 of this Venn diagram. TV makes up 0.8, and I know that this piece right in the middle makes up 0.50. And that's a really good place to start. Well, if this intersection makes up 0.50 and I has to make up a total of 0.6, this region on the left must be 0.1, and using the same argument, the region on the right must make up 0.3. So we can logic our way through that without even really using any formulas, but the way that the formulas would use this is the probability of internet or TV would be the probability of internet plus the probability of TV minus the probability of internet and TV. Now I already know the answer to this. 0.5 plus 0.3 plus 0.1 is 0.9. So I know my answer using my Venn diagram. That's why they're so nice. But I can actually do this with the formula as well. So internet was 0.6, TV was 0.8, but because I double counted the intersection I have to subtract off 0.5. So I have 14 basically minus 5 is 0.90. So that matches exactly with what my picture is saying here. Now if I had to shade this region to represent internet or TV, basically the internet or TV would be this region encompassed by all the circles. I don't know if you can see that very well, but it's yellow highlight. Now we have a little bit of a problem. Remember, the sum of the probabilities has to be 1. And when I look at this, I see 50, 30, and 10. This sums to 90. So somewhere out here is another 10%. And whenever you draw a Venn diagram, the total area encompassed must equal 100%. So don't forget this little piece out here. Okay, let's go ahead and look at another question based on this same data. Let's determine the probability that at least one of these two services comes from that company. So at least one of the two services comes from the company. So we might be talking about something like cell phone comes from the company, or not cell phone, TV comes from the company, internet comes from the company, or both comes from the company. So those are the situations that we're looking at. Now if we have to talk about this in terms of a Venn diagram, let's go ahead and pop up our Venn diagram again and see if we can shade a region that seems to make sense with this. So what we end up finding out is if we talk about at least one of the services, that means at least one would encompass one or two of the services. So again, this would be the same as 1 minus the probability of no services coming from that company. So we end up with 1 minus 0.10 here, which is 0.90. Now where did the 0.10 come from? It comes from right down here in this piece, that 0.10. So if we were to shade this, it would be the same exact shaded region that we had up here. Hopefully this one shows up a little better. Okay, so again, there's a lot of different ways that we can write this. This probability of of internet or TV, that was basically the same as saying the probability at least one of the two services comes from the company, and I could also look at this in terms of the complement. So there's a lot of different ways to write these types of problems, so it's always good to be very clear about your variables. If you're using internet and TV, it's a good idea to use I and TV instead of A and B, because they're hard to mix up if they're I and TV. If they're A and B, I might not remember which is A internet or is A TV. Your book does that all the time, however. So let's go ahead and look at another question from this data set. Let's look at the probability that exactly one service comes from the company. Now this is kind of an interesting question, because you might say, oh, that's easy enough, that's just the circles. Exactly one service. Well, if we talk about exactly one service, I'd have to be careful of this region right here in the middle, because this would be the both. This would be the piece that we kind of need to watch out for. So you might think, well, I can just take our total probability and subtract 0.5, but remember there's a 0.10 hanging out here as well. So remember, what we're looking for here is exactly one. Well, this could happen one of two ways. It could be only internet, or it could be only TV. Now if it's only internet and only TV, what that is basically is just the 0.10 plus 0.3 is 0.40. Another way to write that would be 1 minus the probability of both services, this little wedge in the middle, minus the probability that neither of the services comes from this company. In this case, that would be 1 minus 0.5 minus 0.1, which is 0.40. So there's a lot of different ways to look at these different statements and these different probabilities, and a Venn diagram really helps to kind of bring that out. The next thing that I want to talk about and define and give examples for is the idea of equally likely probability. Now when we talk about equally likely probabilities, a fair coin always comes to mind. Equally likely probabilities mean that all outcomes have the same probability of occurring. So all outcomes, and if we wanted to, we could say in the sample space, have the same probability of occurring. So if we flip a fair coin, the probability of a head and the probability of a tail are both equal to 0.5 or 1/2. So they have the same probability, so they're equally likely. So one example of this would be to flip a fair coin. And all coins are fair, so you have to make sure it's a fair coin first. The probability of a head and the probability of a tail are the same, and they're both equal to 0.5 or 1/2. Another example here is if we roll a fair die. And again, it has to be a fair die. If it's a loaded die, then the probabilities won't be equally likely. So the probability of rolling a 1 is the same as probability of rolling a 2 is the same as rolling the probability of a 3, 4, 5, and a 6, and they're all equal to 1/6. Now notice all of these probabilities are between 0 and 1, and if I talk about summing up these probabilities, they would sum to 1 as well. So equally likely probabilities basically means all the outcomes in the sample space have the same chance or the same probability of occurring. Now there's a couple quick things I want to end with in this section, and one of them is the idea of a contingency table. A contingency table is a really nice way to organize information, and not only organize information and data, but also organize probabilities. So for instance, I could be talking about a particular data set where I recorded their gender and their smoking status. So they could reply with gender, my options would be male or female, and for smoking status my options would be smoking or not smoking, or smoking prime or not. Complement of smoking is not smoking. So if I talked about all these different outcomes, a contingency table does a much better job than, let's say, a Venn diagram in this situation, because this would be a very complicated Venn diagram. So a contingency table allows me to kind of organize this information. So I could put gender on one axis or one side, and then I could put smoking status on the other, and then I could organize my information. So for instance, I'm given some information. We'll say the probability that I have a smoker in this group is 0.25. The probability that I have a male in this group is 0.52. So what we can do is we can start filling in this information into the table. So the probability that a person is a smoker is 0.25. The probability that a person selected from this male, or from this group as a male, is 0.52. Well, we have to look at this pretty carefully. Remember, the sum of the probabilities always has to be 1, but we have two different sets of probabilities here. I have a gender probability distribution, so the probability of male plus the probability of female better equal 100% or 1.0 here. The probability you're either a smoker or a non-smoker better sum to 100% or 1 here as well. So from here I can start filling in probabilities. If the probability that a person selected from the population is a smoker is 25%, it'd be 75% non-smoker. 52% of the population is male, 48% is female. And remember, down and across, these both sum to 1 or 100%. Now the question is this: how do I fill in the insides of my table? And the answer is you cannot fill in the inside of this table right now. You need one other piece of information. And it could be anything. It could be male and smokers. It could be female and smokers. I could look for the number of people, or the probability of people who are females and they don't smoke would go here. I just need one other piece of information to fill in this table. So that other piece of information is going to be the probability that we have a female and a smoker that I've selected. And the probability of that is 10%. So all of this information up here is given. Everything else I can derive from that given information. So female and smoker is 0.10. Well, now I can start filling in this table. I know that this column has to sum to 0.25, so this value has to be 0.15. And I know this has to sum across to 0.52, so this has to be 0.37. And here I can look at two different things. I can either look at it has to sum to 0.48 or 0.75. Either way, 0.38 is the magic number there, and I can figure out what's going on. Now from here I can also answer all sorts of different probability statements. For instance, the probability of smoker or a female. Well, that's the probability of being a smoker plus the probability of being a female minus the probability of being both a smoker and a female. So the probability of a smoker was 0.25, female was 0.48, probability of both 0.10, And it looks like when I sum these probabilities, we get 48, 58, 63, so I get 0.63. Now notice this value of 0.63 does not appear anywhere in this table, but this table represents the probabilities that I can use to use other equations or other formulas to find probabilities. So this table organizes information for me. It does answer and state some probability problems, but not necessarily all. So we've looked at Venn diagrams to order information, a two-case Venn diagram, and then we've also looked at contingency tables. Now what if here we looked at three variables? We looked at gender, smoking status, and let's say some level of health, good or bad health. Well, what would happen? I'd have a three-dimensional table here, or I'd have to take this table and split it out into healthy, not healthy, and kind of split it up that way. So you can see as soon as we get past two pieces of information or two variables, things can get pretty difficult to keep track of. So, speaking of difficult to keep track of, let's go ahead and talk about a three-way Venn diagram. Now, a three-way Venn diagram can actually be written quite a few different ways. We could have a three-way Venn diagram look something like this, where I have events A, B, and C all disjoint or mutually exclusive. I could have something like this, where I have events A and B are not mutually exclusive, but they're both mutually exclusive with event C. We could have something like this, where events A, B, and C have a direct relationship where A and C are mutually exclusive, but B is not mutually exclusive with either with either C or A. So there's a lot of different ways to write this, but a common way that we like to talk about it is if we have events that are not mutually exclusive. So a lot of times a nice way to write that is just like this. So here there is not one event A, B, or C that is mutually exclusive of any other event. Well, here the formulas get a little bit ugly, and I think it's probably easier just to logic your way through this to find the probability of A or B or C. Now the probability of A or B or C would be this, all this shaded region right here on the inside. So that's what I'm trying to find the probability of. Well, it seems like a good idea to start with the probability of A plus the probability of B plus the probability of C. But you can see as soon as I do that, I've overcounted the wedge that's up here in the middle and off here to the left and also off here to the right. So now I need to subtract off those intersections because they were twice counted. But now I've introduced another problem. I added this middle piece in 3 times when I included ABC, and I subtracted it out 3 times when I took these wedges out. So basically I haven't counted it at all, so I need to add that wedge back in, and that wedge is A and B and C. So again, I wouldn't worry about memorizing this formula per se. I think you can logic your way through it for the most part, but we will be working with three-way Venn diagrams in a limited fashion, so I think it's a nice thing for you to be able to work with and keep track of. So from what we started with before, with our ideas of sample spaces and then our rules of probability, that'll give us a good start to get started with counting techniques next.